indices, which I won't repeat here. One can show that all of these n different invariant nonlinear forms commute with all the elements of the algebra. It follows then that the spectra of these must define different irreducible representations because they must be multiples of the identity. All of these objects must be multiples of the identity in any representation. And what that multiple is defines that particular irreducible representation. However, let's look at the particular case, and this is where we begin this lecture, at what we have with the Markov group. I want to look at let's pick any two of the objects L, which I'm going to call LA and LB. I'm writing below the indices which represent the matrix elements of these. Now we're going to find the product of two of these, Lij, Ljk, and that's going to be the matrix product of any two elements of the Markov algebra. I now want to perform, of course, matrix multiplication means I sum over this J, which I've written here. I now want to look at a summation over I of that quantity. Well, I can invert these two sums so that the sum over I comes inside and the sum over J is out here. But the sum over I means sum over all rows for any given column J. Well, for all of the L's, even in n dimensions, no matter how complicated, for every single L we have, that sum vanishes. Therefore, this is equal to 0. Therefore, the whole term is 0, and when we sum it, we get 0. But since such objects constitute all independent ways in which one can have matrices that sum over all the rows, giving you a 0, it follows, therefore, that this object itself is expressible as a linear combination of the L's of that order, and therefore is already in the LieAlgebra. Now this is a very, very important and powerful concept here. It basically says that if I take the product of any two L's, even in n dimensions, no matter what they are, just call them A and B, and I perform the matrix multiplication over J, summing over J, and then I say, what is the sum over the rows of the resulting matrix? I can invert the two summations, bring this summation in here where it sums over all the rows for any given column, and with this all by itself right here, for any one of those transformations, this vanishes. Therefore, it follows that this is equal to 0. Therefore, all products of the generators are expressible by the generators themselves in a linear form. Now, what does that say? It means they're already in the LieAlgebra. If they're already in the LieAlgebra, there is no nonlinear product that's not in the LieAlgebra, that's different. Therefore, there are no Casimir operators. They do not exist in any level, in any dimension for these Markov generators. So number 6 is a very important property. The next thing that we want to look at is the lack of an inverse. Well, that's very easy to understand with these transformations, because you'll recall that we wrote e to the lambda Lij, and we formed a group with that, with using the minus Lij giving the inverse to lambda ij Lij. However, if we have a lambda ij that's negative, then that's not allowed because they will lead to the mij's, which are negative. We showed that with our infinitesimal transformation, and thus which do not preserve both the summation and the positive, or I should say the non-negativity of all possible elements that could be acted upon. So if I were to allow negative lambdas anywhere in the LieAlgebra for the Markov transformations, what would happen is that there would exist some vector with some component such that all of the sum of all the components would be equal to 1, and they were all non-negative, but they could be carried into another one where the sum was still equal to 1, but in which a component was negative. And that's not allowable for the probabilities. Therefore, no one of the lambdas can be a negative value. This is where the inverse goes. So the Markov transformations must not allow, if they're going to be physical, that part of the Markov Lie group or Lie algebra that has any negative parameters. Now, if we stop and think about how large a number of elements that is, it's the preponderance of the algebra itself. Because if we think of the algebra as A times the first L plus B times the second L plus C times the third L and so forth, then all of those A's, B's, and C's must be non-negative. Well, that leaves out a huge portion of the space. In fact, one is allowed for real Markov transformations to only take that part of the Lie algebra where all of these parameters are positive, and that is just the positive hyperquadrant of the Lie algebra thought of as a linear vector space. So we now know why these transformations do not have an inverse and why they're not physical. And therefore, why the transformations lead to diffusion without having an inverse. Because you can't undo them. You can't go back. The next property of the Lie algebras that I want to look at is the following. I want to take the most general possible Lie algebra of order 2. And such an algebra is made up of two generators, A and B, such that AB minus BA is in the algebra. Therefore, it's alpha times A plus beta times B, which is the commutator of A and B. I now want to define two new elements, X and Y. These are two new basis objects, basis elements for the algebra, where I define it as X is A over beta, and Y is defined, and that's a definition, as B over alpha, where alpha and beta come from here, and A and B come also from here. Then it follows that A is equal to B times X, and B is equal to alpha times Y. Now, if we plug A and B into this expression, we get the following. We'll get alpha times beta, which factor out commutator of X and Y is equal to, and of course what we get here is by plugging in this A here, we get alpha times beta times X, and this goes in here, and this right here gives us beta times alpha times Y, or alpha beta times Y. Therefore the alpha beta may be pulled out, and we get alpha beta times X plus Y. Well, now the alpha beta cancels on both sides of the equation, and we get X commutator Y is X plus Y. That means that no matter what Lie algebra we may have, we may reduce the commutator of the two elements to the form which is the sum of the two. Now that includes the case that we have with our Markov Lie algebra. And we can do that very simply by saying we're going to make alpha is equal to plus 1 and beta is equal to minus 1. So we start with the Lie algebra L12, L21 is L12 minus L21 by taking L12 new, or the bar, as the negative of L12, and this one is the same. Then we would get a minus sign here, a minus sign here, a minus sign here. Obviously, therefore, we can multiply by minus 1, and we get the bracket commutator of L12 with L21 in the new reference is L12 plus L21 with bars over them. So we have cast our Lie algebra into this form right here. Thus it follows that every single Lie algebra of order 2 is equivalent to a Markov algebra of order 2. And therefore it's equivalent to this form, or equivalently can be written in this form up here. Now, the ninth property I want to look at is, since the Markov Lie algebra is defined by the commutation rules and consists of elements of this form, however, valid Markov transformations arise only from these positive hyperquadrant, where the alphas are positive and the betas are positive, and that, as I mentioned before, removes the inverse and makes this a mathematical structure which is different from a Lie group. It's a Lie group, but it's a Lie group without the inverse. Such an object is called a monoid. Not a semigroup, not a semi-algebra, not a loop, not one of the other names that takes out one of the four characteristic properties of a group, except a group without the inverse is called a monoid. And that's what this is. So we have been looking at Markov monoids. It just sounds kind of strange because we rarely hear this word. And that's a Lie algebra that does not have the inverse. I want to summarize some of the primary properties of this Markov Lie algebra. The first is that each of the off-diagonal positions I naught equals to j in n dimensions for square matrices defines a Markov generator. And that can be defined formally as Lij is equal to a delta I alpha, and this should be a delta j beta, minus a delta I beta delta j beta. Now, this formal expression in terms of Kronecker-deltas is just a formal way of saying that the alpha beta matrix element of the object that we call the Ij generator will have a +1 exactly when I is equal to alpha and j is equal to beta. And it will have a -1 when both I and j are both equal to beta, the second index, which puts it on the diagonal. So this defines the +1 and this defines the -1 in this form. Using those Kronecker-deltas, one can actually formally work on the commutation rules for n-dimensional Lie algebras of the Markov type. Secondly, when those generators are joined with the abelian generators Lii, whose matrix elements are alpha beta, those can be defined as having a 1 when alpha is equal to I and when beta is equal to I also. And that puts a +1 at a position always on the diagonal, because both are equal to I, for all the different possible n different positions along a diagonal. That gives us a complete set of generators of all the n by n matrices and serves as a basis of the general linear group in n dimensions over the reals. The next property that I want to look at is that all Markov transformations that are continuously connected to the identity arise in the transformations m of lambda is equal to e to the lambda dot L, or more formally lambda ij times Lij, where the lambda ij are real non-negative numbers, and they are n squared minus n of these numbers that span that positive hyperquadrant of this Lie algebra. Remember that a Lie algebra is a linear vector space. So in this linear vector space, you're looking at only one quadrant out of the 2 to the nth power different quadrants that you have here. The core value of the formulation that we have presented, number 4, rests with the fact that the Markov transformations are in one-to-one with this positive hyperquadrant space, lambda ij. And in essence, what that means is it's very easy to specify, by specifying non-negative lambdas, what these transformations are. It was so simple, and it kind of fell out in front of us, and it seems so obvious that it's very easy to dismiss it as unimportant or as trivial. But you see, we're able to separate out those transformations out of this whole Markov-Lie group that are admissible for actual Markov transformations simply by saying all the parameters have to be in this positive hyperquadrant. And that's what makes it useful. That was possible because we defined our generators very well in the first place. We said we'll rob Peter to pay Paul. We'll give a fraction of what somebody has to somebody else. We'll give a fraction of the people in New York to California, and a fraction of the people in California to Kansas, and so forth. And that's what made this useful. The resulting system, as we have mentioned, is a Lie algebra, or Lie group, without the inverse, and that is called a monoid. So the formal thing that we have reached by throwing away all of the negative lambdas is a Lie algebra monoid, I guess one would say, or a Lie monoid. We conjecture in these lectures that follow that the concepts are going to be deeply related to information theory. And that is the reason that we have this special interest in these Markov transformations. With the risk of belaboring a point, I want to discuss for a few minutes how in the next period of time, in the next few lectures, we will make that connection between information theory and these Markov transformations. Perhaps at the core of it is the fact that these transformations represent a diffusion. And we saw that with one of those transformations. And we saw that any of these transformations that are going to act mix up the states in a way that we cannot undo them with an inverse transformation. Well, this really is very much like the problem that Einstein worked on when he looked at the random walk. And he said that you can take a walk, a step like a drunken sailor, away from a light pole, one in this direction in any random direction, then another one in any random direction, each with the same size. And as that happens, one begins to diffuse away from the lamp pole, so that on the average you have some probability of being further and further away from the original position just by making all of these random and stochastic transformations. Perhaps another way that I could emphasize this point is to imagine that we have an aquarium tank. And the aquarium tank is divided by a membrane that goes exactly through the middle, dividing the left side of this tank from the right side of the tank, and we have an equal amount of water on both sides. One of those sides has ink on it, and so we have real inky water, dark, blackish water on one side, perfectly clear water on the other. If the ink is on the left, we call that a 1. If the ink is on the right, we call that a 0. So we can represent binary information by looking at whether the ink is on the left or the right. Now, in the theory of quantum computing, one might do a similar thing with the spin of a particle, and we could do the same thing here. We could have a particle, and if it's spinning up, or 1, then that says yes, or true, or 1. If it's spinning down, we could say no, or 0, or minus, or false. And that would give us the lowest form of information, namely the bit of information. So our aquarium tank, or the particle with spin, could represent information in its lowest form. Now let's imagine that we punch a tiny hole between the left and the right side so that there is a certain probability for the water to flow from the inky side to the clear side and from the clear side to the inky side. That is exactly the diffusion transformation with equal mixtures of these two L's, L12 and L21, that we spoke of earlier. And one can see that after different periods of time, as time evolves, the inky side gets clearer and the clearer side gets inky. You could ask yourself, at some point, can I really tell which originally was the side with the ink and which was the side that was clear? Well, at some point in the future, we will pass the level of our ability to judge the clarity of the water in one side and how it differs from the other, and at that point, there's no more information that's present. In fact, to a certain extent, we've been losing information all along because this tank has been becoming more and more diffuse in the way that the information is spread between the two sides, and it's exactly like a particle that no longer is spinning totally up or totally down, but spins more and more to the projection in the middle. And we have said that information has been, quote, lost on a continuous basis here, but how do we define information? Our fundamental definition of information is, in fact, a 1 or a 0, which represents 1 bit. How do we define a smaller unit of information, as would be applicable here, to what is being lost with the Markov processes? Well, we will find in the lectures that follow that this is a very diverse and interesting field. We will first be looking at a concept that has emerged in many other areas of science called Fibonacci numbers. Then we'll be looking at fuzzy logic and the concept of fuzzy or numerical uncertainty. And we will then follow that with systems of networks and applying some of our knowledge of these Markov processes to network theory. So next we will do Fibonacci numbers.